Hello everyone and welcome to Vibrations and Acoustics. Today we're going to do a problem of a forced excitation due to a forcing function at the base as opposed to actually at the mass. So go ahead and read this problem. Basically what we have is the ground shaking and we have some mass up on two struts that equate to a spring basically holding this all together. So if you simplify the system, you've got the block of ground moving back and forth, you've got the spring metal bar up here, and then you also have the mass. If you want to reduce this even further, you can say this is the direction x of the main mass x is actually equal to this times a spring. Because if you think about it, this base is moving back and forth, this thing's going to shake, but only as well as these metal bars transfer the force through, and they behave as a spring. So you've got k of x minus xg is equal to the force exerted by this spring. The reason it's k of x minus xg, if you've got this ground moving some distance and then this mass moving some distance, the spring is a function of the relative distance between them. So you take however far the mass is minus however far the ground is, and you'll actually know where it is, because this whole thing could be adjusted over here, and mass is going to do basically this kind of a deal right here is what's going to happen. And you can see that the top of my pen is reliant on where the base is. Like at this point, they're at the maximum distance, but at this point, they're at the same distance, and it's all dependent on where my pen is moving. But this is exactly the kind of system that we have. And if I had something softer than this pen, like a piece of string or a piece of rubber or something, you would be able to see the spring action much more easily. But that's basically what we're working with. So in order to get the equation of motion with this so that we can kind of start out and see what we're working with, since it's a translational system, you start out with some of the forces. And this is going to be a really simple equation because it's just an mx double dot. Sum of the forces equal to mx double dot. So we've got negative k of x minus xg, because we're assuming this direction is negative basically, is equal to mx double dot. Since we have no dampers or any other kind of external forces, we don't really care too much about this. And this is only for the mass. This is not including the ground. You're saying, well, there's a forcing function on the ground. Not really, not yet at this point. But in order to relate all this stuff together, we're going to go a little bit further. And actually, the equation of motion, the final equation of motion, will be mx double dot plus kx, which is equal to k xg, okay, is equal to k, the amplitude of the ground vibration, sine of omega t, and this was given to us as f naught sine of omega t. So, the reason this is like this is because we have the mass moving, the standard thing we brought over to the side. We brought in the k, this is a minus, not an equal sign. Sorry, there was an error in the notes that I didn't catch on. You take mx, you distribute this kx through here, and you end up with kx plus minus kx plus kxg up here. Move it onto this side, the signs flip, you have this. And then these are related to k by the relation of k by the forcing function, because the forcing function only transfers what the k is allowed to transfer through to it. Okay, so this is all, so basically whatever force is applied up here is also the force that is applied down here, and it's related by the k in the middle there. Alrighty, so let's go ahead and solve this. We're looking at this equation of motion where we have the mass moving and then the k with relation to the displacement of the mass is equal to the force of k times the relation of the displacement of the ground. This is how this is. The displacement of the mass, the forces related to the mass, are equal to the forces related to the ground because they are a connected system. Okay, so for the steady state solution, steady state, which is the particular part of any differential equation if we were to solve this totally from scratch, this is xss sine of omega t. Alrighty, so then xss is equal to F naught over K. And this is an equation hopefully you've been exposed to before, squared. And we know that F naught is, from this equation up here, F naught is equal to K of xg. So we've got kxg all over K, which we're just going to cancel these K's. This is equal to something, something is equal to xg, excuse me, 1 minus r squared. Okay, so that's your XSS. Now we know that omega n is equal to the square root of K over M. And we know that this is equal to the square root 0.5 times 10 to the 6 newtons per meter, all over 2,000. If you solve this out, you'll get 15.811 rads per second. Just get this up here so you guys can see it, rads per second. So then R is equal to omega over omega n. Omega was given in this problem within the sine function as 200 radians per second. So 200 rad per second all over 15.811 will equal 12.659 rad. Well, no, that's just a ratio, sorry. Has no units. Okay, so then XSS, since we now have R, is going to equal 15 millimeters all over 1 minus 12.6592, which will equal negative 0.0942 millimeters. And this is the amplitude, the steady state amplitude of the system. So now, in order, excuse me, so then the amplitude of the floor with respect to the ground will be basically x of ground plus XSS, which in this case is going to be 15 plus point, or minus, sorry, this is minus XSS. So 15 plus, since this is a negative, 0.942. So then the total amplitude of the floor vibration with respect to the ground at any given time will be 15.0942 millimeters. And that is your final answer for this problem.